Okay, this board's pretty full of stuff. You make your own decision about what it's full of. But here's your basic quadratic function, the y equals x squared function. Same thing we looked at in the first video on the basic functions. We have the domain somewhere. I don't think I wrote down the domain of this thing. No, I didn't. Okay, anyhow, we have the basic function. We know what its domain is, -2, -1, -1/2, 0, 1/2, 1, 2. Its range of the basic function is 0, 1/4, 1, 4, as we've seen. If you do the extended basic function, its domain is -∞ to infinity, as we saw. Any number from, I'm pointing the wrong way, any number from -∞ to infinity in the x-axis is in the domain of the x squared function. And its range is from 0 to 4. And I had these kind of color-coded. I didn't use the right color in this one. Okay. Now, the basic exponential function, y equals 2 to the x, has a graph that looks like this. You can make the graph yourself. You can plot these points. You can see where they are. Okay. The domain is -2, -1, 0, 1, 2. We don't include the 1/2 in the domain of the extended of the basic exponential function. Okay, I see where I address domains down here. So here's the domain of the basic 2 to the x function. I had to slide that word basic in there because I kind of left it off. And that's -2, -1, 0, 1, 2, as I said. And here's the domain of your basic x squared or x cubed function. Both x squared and x cubed, as we saw on the tables, can be evaluated for any real number. So in particular, among the standard points, we can include them all. So all these points are included in the domain of x squared or x cubed. Okay? The 1 over x function. Okay, now remember that the 0 is excluded from the domain. There is no point on this graph of the basic reciprocal function where x equals 0. And x equals 0 here and everywhere above and below. In other words, x is 0 on the y-axis, so that you have no point on the y-axis. Now people, when they get these 3 points here and these 3 points here, which you'll see clearly if you graph the thing, the -2, -1/2, the 1, -1, the 1/2, -2, and the 1/2, 2, and 1, 1, and 2, 1/2 points. They want to follow this curve here, okay? And then they want to somehow get over here and go through the y-axis and get up here and connect everything. Well, at this point, coming into pre-calculus, you should know better, but most people don't. So if you don't, you've got a lot of company. You got to fix that. You can't have a point on the y-axis. There's no justification for trying to connect what happens over here to what happens over here, because to connect these two parts of the graph, you would have to have a point where you go through the y-axis. You can't do it, so there's no point in trying, and it'd be totally wrong anyway. Because if you think about it, as x gets closer and closer to 0, x goes into 1 more and more times. There's no limit to how close you can get to 0. There's no limit to how many times x can divide into 1, so there's no limit to how big y can get. So y just keeps getting bigger and bigger and bigger as x gets closer and closer and closer to 0. And on the negative side, same thing. X gets closer and closer to 0, but it's negative, so it goes into 1, well, a negative number of times. It's unlimited. The graph just keeps going here, and you get these asymptotes we get an asymptote at the y-axis. It's an asymptote where you approach the asymptote from the positive numbers here and from the negative numbers on this side. Okay, and the reasons for that should be very clear. I'll go into more, again, in the more detailed explanation. So you get an asymptote at the y-axis. It's a vertical asymptote. should have said vertical asymptote, and I didn't have room to write vertical in there. So there it is. Its domain is, well, the numbers, let's see, where is it? Domain of 1 over x, and it's the same for the domain of 1 over x squared. You can evaluate it at every one of the points in the standard list of 7 x values, except for 0. So there it is. There's a domain of 1 over x. It's also a domain of 1 over x squared. The difference between 1 over x and 1 over x squared is the numbers get bigger. You know, if x equals 1/2, x 1 over x squared is 4 instead of 2. So numbers here get bigger as you approach, as x approaches 0. And they also are positive on both sides of the axis, because when you square a negative number, you get a positive number that's then divided into 1, and you get these values. So the graph looks like this. And again, you don't get up to 4 and here, and then try to go across the x-axis. That's not what happens. And you don't try to cross, and I said the x-axis, you don't try to cross the y-axis, because there's no point on the y-axis. You can't evaluate this when x equals 0. There is no point on the y-axis. Okay, so the domain for both of these functions is, as we say. Okay. For the basic cubing function, again, we already said the domain consists of all the standard values, and the range is the set of y values, which are -8, -1, -1/8, 0, 1/8, 1, and 8. So here I've written out the range of the basic cubing function. -8, -1, -1/8, 0, 1/8, 1/8. Okay. There are graphs. You can draw your own graphs and verify that they look like this. You can look at my more detailed explanation of the shapes of the graph. Make sure that if you're doing 1/8, you get 1/8, not 1/2 or 1/4, because this graph flattens out a whole lot if you do the graph accurately. Okay. The extended basic functions are the ones with the curves. We've talked about this one. The extended basic function here, the values go from the -2 value of the 2 to the x function, which is 1/4, all the way up to 4. So the range of the extended basic function, there it is 1/4, 4. All values from 1/4 up to 4. You could shade those values on the y-axis if you want. They go from 1/4 all the way up to 4. That's the extended basic function. It starts here and ends here. And, you know, when I wrote that down, I was somewhat careless. I don't like to find these errors. That was an error in notation, because that means there's something misleading on the more detailed video. Be the closed interval from 1/4 to 4, not the set 1/4, 4. So we want to make sure we kind of correct that. Okay, so there it is. And then you have the complete basic function. Okay, the domain of the complete basic function, complete basic 2 to the x exponential function. Well, the domain is from -infinity to infinity. You can do 2 to the x for any value of x. As x becomes further and further along the negative line, you get bigger and bigger negative numbers. 2 to the x becomes smaller and smaller because you have the reciprocal thing. So the graph approaches the x-axis, doesn't reach it, never actually gets 0 by plugging any number into 2 to the x. But you get very close to 0. So you have what's called a horizontal asymptote on the complete basic function. And then the function goes off, gets very, very steep. It looks practically vertical very quickly. but it never is exactly vertical. And it looks like I didn't write down, okay, yeah, I remember what I did. Okay, so let's go over here. Yep, don't have it there. Didn't have room to write the ranges and the complete functions. So I'll put this up here for the moment. Okay, the domain for the complete basic exponential function is negative infinity to infinity, as I said. The range is any number that's greater than 0 and all the way up approaching infinity. So for your basic exponential, we have the open set 0, infinity. Open because 2 to the x can never be 0. Okay? Now for the complete basic reciprocal function and the complete basic reciprocal square, these are ranges. Remember, the domain can't include 0. Now, this is getting a little clumsy, but I have to do it. So, for this function, the complete function just continues on, just continues on down here, asymptotic to the y-axis and asymptotic up here. And it continues on as an asymptote to the x-axis, because when x is very big, 1 over x is close to 0. Okay? Now, if x is very big in the positive direction, 1 over x is a positive number greater than, close to 0. In the negative direction, a big negative number, 1 over x is going to be a negative number very close to 0. So you're going to have horizontal asymptotes, good heavens. I hate to admit this, but I misspelled vertical there. I did it right here, and I don't know how I wrote it like this. I see it a lot. I think I spelled it that way once, got embarrassed and didn't do it again until now. Okay, this is vertical with an AL. Okay, back to what I was saying. You have a horizontal asymptote here because as x gets big, 1 over x approaches 0. And 1 over here, but it's negative. For the 1 over x squared function, it's the same thing, but of course, the numbers are all positive, so you have an asymptote with positive numbers approaching 0. Okay? So you have horizontal asymptotes here, and you have horizontal asymptotes here, but I didn't have a good way to label it. So we see that the domain of the complete basic reciprocal function or reciprocal square function, you can evaluate 1 over x or 1 over x squared for any number at all except 0. So the domain is going to consist of the interval negative infinity to 0, union the interval from 0 to infinity, the open interval in each case, which excludes 0. And that's the case for this function and for this function. That's the domain. The range for this function consists of all negative numbers or all positive numbers, because any number, for any point on the negative y-axis, you have a corresponding point on the graph. Okay? And on this side, you see that you can get any positive number. Any number except 0 from negative infinity to infinity. Negative numbers on this side, positive numbers on this side. Looking at the range, looking at the y values. Here, we get any positive number. We can't get 0. No number divides 1 0 times. But we get all the positive numbers. So the ranges of these functions. Again, ranges for the complete basic reciprocal function, negative infinity to 0 and 0 to infinity. Okay, the negative numbers, the positive numbers. For the complete basic reciprocal square function, 0 to infinity. And for the complete basic cubing function, which I'm not going to talk too much about right now, it's pretty clear that you can cube any number, and if you look at the graph, you can understand clearly that you can always find a number to cube that'll give you any positive or negative number. So that's the way that one works. Okay, so that's a fairly complete discussion of the basic functions, their domains, and their ranges. The basic functions, the extended basic functions, the complete basic functions. You want to have that picture. You want to be able to draw these graphs and reproduce all this information.